All right, so significant digits again, this time scientific measurement and how that relates to significant digits. It's going to be on page 25. So flip over to 25 again if you are not already there. And we are continuing to look at making and analyzing measurements to communicate levels of accuracy and precision using significant digits. So that's what we are tackling today. So first, uncertainty in measurements. Why are we uncertain in measurements? Well, when you take a measurement using a manual instrument, you're going to write down all of the digits the instrument gives you plus one uncertain digit that you estimate. So that's like what we did with the graduate cylinders and what we did with the rulers. And when you use an electronic device, those already do that estimation for you, okay? So then if we are looking at something like this, then we could measure, and my graduations are by 1, so I could measure to the ones place and then 1 decimal place. So if my measurement was, say, right here, that is at the 9, so I could measure 9 for sure, and then 1 uncertain digit, 1 estimated digit. So 9.3, I might say, for that measurement. If I have something that looks like this, then I've got more graduations between 1 and 2, so I can measure more accurately. So if I've got, say, a measurement right here, then that's going to be 1 for sure, 0.1, and then maybe 4, because it's almost halfway between the two. So 1.14. That's how you're measuring with significant digits. But if I have only by the tens place, then if I've got a measurement right there, just after that last tick, then that's going to be 1, 2, 3, 4, 5, 6. So that's 160. But it's a little over 160, so I can estimate one more, so 162, I might say. Okay? So then let's look at a ruler here. It's going to be, if I only have this one graduation at 1 meter, then it's a little over halfway, so I could say 0.6 meters, but I can't be any more precise than that. If I've got a slightly more accurate, a slightly more precise ruler, then this is where I could get one more decimal place, so 0.61 meters. And if I had my millimeters or my centimeters measured out, then I could get to 0.607 meters, because I can measure one estimated digit more than what my graduations show. So why are we uncertain? So instruments are never flawless. They always have some sort of estimation that go into them, and that's going to be in a digital form. The last digit on that value is going to be estimated, and scales are human estimation. So we can estimate on things like rulers and balances and things like that. So reliability in measurement, we want to make sure that things are precise. Precision means that you can consistently get the same result over and over and over again. So your values that you get, the measurements you get, are close to each other. And accuracy is being able to get close to the accepted value or the standard. So if your average of all of your measurements are really close to the accepted value, then that's going to be an accurate measurement. It doesn't necessarily matter so much for accuracy whether or not they're close to each other. So let's look at some examples. So if you are looking at your bathroom scale, then we kind of want those to be pretty consistent and accurate. So we would like some precision and accuracy with those. But if you were talking to an airline and the luggage that you bring onto the airline, they are very, very particular about how much baggage they can carry, because they are limited on how much weight they can carry on those planes. So they need a much higher level of accuracy and precision with their measurements. That's why when you go to the airport, if you get your luggage on there, you see that your scale that you're looking at is more precise. There are more decimal places. So precision versus accuracy. This right here, you see that my values are all in the top right of this target, and they're all really close to each other, but they aren't close to the bullseye. They aren't close to the accepted or standard value. So that's going to be high precision because they're really close together, and low accuracy because they're far from where they need to be. And if you've got something closer to this where they're a little bit more spread out, so that means that there's lower precision, they're further from each other, but they are averaging around that accepted value, the bullseye, so higher accuracy. This one right here, they're really close together and all right on top of that bullseye, so that's going to be high precision because they're close to each other, high accuracy because they are close to that accepted value. So let's try one here. Looking at this first one, we've got 8.34, 8.37, and 8.41. Accepted value is 8.65. So to figure out if they are close to each other, we just look at the numbers themselves. Are they close to each other? 8.34, 8.37, 8.41, all those are just a couple of hundredths off, so those are high precision. And then we've got to figure out, are they close to each other, or close to the accepted value, the expected. So what you're going to do is you're going to take the average. Do you remember how to make an average? Average is the sum divided by the number of numbers. So in this case, we've got 8.34 plus 8.37 plus 8.41 divided by how many numbers did we have? 3. So we've got divided by 3. That'll give us an answer of 8.373 as my average. And then we compare that. Is that close to my accepted value? Sorry, that's off the screen. Is that close to my accepted value? And it isn't super far off, but it's definitely not close. So I would say somewhat low accuracy. Then we've got 8.34, 9.24, and 8.8. Expected is going to be 8.65 again. When I do my comparison of the numbers themselves, they are pretty far away from each other. They're like at some points almost a whole number away, so that's pretty low precision. And go ahead and try to get the average of those 3 numbers. Pause the video, get the average of those 3 numbers. When you get the average, you should get an average of 8.793 repeating. And comparing this to my expected, that's pretty close. So this is actually a pretty high accuracy set of data. Okay, then this last one, go ahead and see if you can make a prediction, calculate that out and see whether you think these are precise and whether you think these are accurate. All right, now that you've got that figured out, we look at the numbers themselves. Are they close to each other? Yes, they are, just like in the first one, so high precision. Find the average. When you do that, you get 8.373 repeating as my number here, and compare that to this, and it's even further away. So this is what I would call very low very low accuracy. Okay. All right. Next, we've got significant figures. So significant figures, again, like I've said a couple of times, this is hugely important. Helps us a ton. So first, what does this matter? So how much money do you have in your pocket or in your purse? Okay. And we can, depending on who we are and how we address these things, we might answer this differently. Some of us might say about $20. Other people might say, I've got $15.37 because we know exactly how much we've got. So sometimes we estimate, and sometimes we know the answer more accurately. That's what significant digits allow us to do. So how many people are in the U.S.? Well, we've got a pretty difficult job there to be able to answer that question, because it's hard to know exactly how many people, because you can't go and actually count one by one every person. How old are you? We can know that really confidently because we know exactly when you were born and we can figure that out. So there are different problems that might require a different level of precision. And then what time is it? Well, we can check the clock, and clocks measure really detailed, really precise measurements of time. So the rules for significant digits, this is what you will want to make sure you get down. So all non-zero numbers, count all non-zero numbers as significant figures. So 1, 2, 3, 4 has 4 significant digits because 1, 2, 3, and 4 are all non-zero digits. Non-zero just means anything other than 0. Then count zeros that are in between non-zero numbers. Any zeros that are trapped, like this 0 between the 7 and the 8, that's going to be a significant digit, a significant figure. So this 708 has 3 significant figures. Then 1008, 1 is a non-zero, 8 is a non-zero. Those zeros are trapped between it, so also significant. If a number is less than 1, count all the numbers after and including the first non-zero number. Do not count the zeros to the left of the first non-zero number. So, example, 0.000987. So you're going to look and find my first non-zero, and that is this 9, and I'm going to count everything after it. So that's 3 significant digits. The zeros in front are not significant, okay? So 0.009870, same thing. First significant digit is that 9. 1, 2, 3, 4. Everything after that 9 is going to be a significant digit. So that would be 4 significant digits. So 0.9 has 1 significant digit. How many significant digits would 0.09 have? How many would 0.009 have? Well, in both of these cases, we check for the first significant digit, and first significant digit is 9. We count it and everything after, so 0.09 has 1 significant digit, 0.009 has 1 significant digit. Okay? Let's see if that changes. 0.0009 also has 1 significant digit. Also 1 significant digit because that 9 is the first non-zero, nothing after it. It does not matter how many zeros you have in front of it. It matters the number, the first non-zero number, and then all of them after it, if it's less than 0 or less than 1. Okay? So if a number is greater than 0, and no decimal point is written, count only the non-zero numbers and zeros between them, non-zero numbers. So if we're looking at 48,000, it has 2 significant digits because we're looking 1, 2. These zeros behind it are insignificant. They are not part of the significant figures. Then 408,000 has 3 significant digits because these are non-zero. and the 0 between it is trapped, it's also a significant digit. None of the others are, so that's 3 significant digits. Then 9 has a single significant digit. 90, so we check. It's got the first non-zero, and then everything after it, because there's no decimal, that is no more significant digits, so only 1. 900, same thing, has only 1 significant digit. 9,000, only 1 significant digit. 90,000, 900,000, and 9 million all have only 1 significant digit because it has only the non-zero 9, and then everything after it is a 0 with no decimal point. So significant digits, one thing that I need to emphasize here is you'll never want to confuse significant with important, okay? Important is different than significant. If you look at 9 and 9 million, they have the same number of significant digits. There is huge difference between them. So what I always say is if I work for an hour and I make $9, right? Then that's very different than making $9 million. But if I work really hard my whole life and someone owes me $9 million and they say, okay, well, the only thing that's significant is the 9, so here's $9, you're going to be angry, as you should. So always remember that significant and important are different. So if a number is greater than or equal to 1 and a decimal point is written, then count all of those digits that are there. So this number right here has 7 significant digits. All of them are non-zero. Then 1000.000 has 7 significant digits. That decimal tells us that we have measured all of these zeros. If I was missing that decimal, none of those zeros would count. Because I have the 0, that tells me that I've measured them. So they are significant. So 9 million has 1 significant figure. 9 million decimal has 7 significant figures. Okay? So, trick for remembering this. We've got the Pacific side. So if you see that a decimal is present, start on the Pacific side and find the first non-zero digit. Okay? Then start counting. And so if we look at a number, we've got 900.1. Start on it is present, so we're going to start on the Pacific side, which is the left. That's 1, 2, 3, 4. Okay? We find the first significant digit, the first non-zero, count left to right. Then if you're on the Atlantic side, then that's absent, no decimal. So you're going to start on the Atlantic side and find the first non-zero digit and then start counting the other way. So if I've got 900 with no decimal, then I find the first non-zero from the right. That'll be on the 9. And then start counting to the left. That's the only one, so that would be 1 significant digit. If I had 180100, then I would find the first significant digit, no decimal place, so first significant digit from the Atlantic side. So that's going to be right here on the right-hand side. That's the first non-zero. And then 1, 2, 3, 4. So that would be 4 significant digits. Okay, then let's try a couple. We've got uh, 6,903. We've got 3 non-zero with a trapped 0, so that's going to be 4. Then you guys try the rest of these real quick. Pause the video. Try to come up with how many significant digits for each of these. Okay, welcome back. You've got 6,903. Again, that's 4. 56.02. that decimal is present, so you find the leftmost, the Pacific-most digit, which is the 5. 5, 6, 0, and 2 are all significant, so that is 4. Then 56.0, there is a decimal, so that 0 is going to count. That's going to be 3. The decimal is absent, so this one you're going to be starting on that Atlantic side. You find the 6 is non-zero, so that and my 5 are going to be significant for 2 significant digits. Decimal present, start on my Pacific side, that's going to be my 3. 3, 4, 2, 1 are all significant, so that's going to be 4 significant digits. 4.00500, decimal present, so present is Pacific, that 4 is the one we're going to start with. All of those are significant, so I've got 6. Then 6890 is going to be 3, and that last one we will have 5. Okay. Again, we've got accuracy and precision. We have uncertainty in measurements and significant digits, and then remember that you need to have taken notes on this. And again, thank you guys for being awesome. Let me know what you guys have is questions when you get to class.